Good day! For this video lecture, we would be learning about torsion in composite shafts with initial mismatch and how to apply the equations that we have developed for torsion for composite shafts. We will learn about the relationships between the torques of each type of material and the angle of twists of the composite shaft. We have already encountered composite shafts in Chapter 2, and the principle is very similar. Remember that composite shafts are made of two or more different materials wherein one material encloses the other, and the two materials are either welded fully together or attached at both ends. The composite configuration can also be called the parallel configuration, whereas the compound configuration can be called as the series configuration. In this case, or in this figure, we have material A and material B, wherein material A encloses material B, and they are welded together. When a torque is applied to the shaft, the two materials twist together, or they move as one. Hence, their angle of twists are equal. Meanwhile, the internal torque felt by the shaft is shared between the two materials. When we write that in equation form, for composite shafts, the internal torque is shared between the two materials. Hence, your T internal is equal to TA plus TB. And as I've said earlier, the angle of twists for both materials are equal. Hence, phi sub A is equal to phi sub B. Now, do not assume that TA is equal to TB or the internal torque is equally shared between the two materials. Most of the time, TA is not equal to TB. What would be the relationship between TA and TB? Use the equation phi sub A is equal to phi sub B to get the relationship of TA and TB. However, if it is indicated in the problem that TA is equal to TB or TA and TB has a certain relationship, use that relationship. Note that you will be using these equations for the next sample problem to be discussed in the next video for the series set. Now, Vice President Leni Robredo uttering these equations is fake news, but that doesn't make these facts fake news. As I've said earlier, you will be using the equations that I just recently discussed in sample problem 6. This sample problem has a slight twist from the basic composite shaft problem because initially, the steel shaft and the aluminum shaft are not joined together at one of their ends. We need to twist the steel shaft so that the holes for the pin would connect the two shafts will align. So I will read the problem. The steel rod fits loosely inside the aluminum sleeve. Both components are attached to a rigid wall at A and joined together by a pin at B. Because of a slight misalignment of the pre-drilled holes, the torque T0, which is equal to 750 Newton meter, was applied to the steel rod before the pin could be inserted into the holes. We are asked for the torque in each component after T0 was removed. Use G equal to 80 GPa for steel and G equal to 28 GPa for aluminum. The given is also in the figure. In this figure, the blue circle represents the cross-section of the steel shaft and the gray circle represents the cross-section of the aluminum shafts. The two white lines represent the holes that are misaligned. As stated in the problem, initially the holes in the steel shaft and the aluminum shaft are misaligned. Hence, the equations we discussed earlier cannot be used in this problem. For the holes of the two shafts to align, we need to apply a 750 Newton meter torque to the steel shaft. And you can watch that the steel shaft would twist for the holes to align. We can determine the angle of misalignment or mismatch using the equation phi or angle of twist for the steel equal to TL all over JG. We use the 750 Newton meter torque because it's the torque that will remove the misalignment. Note that we are using 40 millimeters as the diameter in the computation for the polar moment of inertia, J, and 80 times 10 to the 9 Pascal or 80 GPa as the modulus of rigidity because it is the steel shaft that twists for the holes to be aligned. The aluminum shaft is not twisted. The angle of the mismatch is 0.112 radians. Now, after the mismatch is removed, the pin can be inserted into the matched holes. After the misalignment is fixed, the 750 Newton meter torque is also removed. What will happen to our shaft? At this point, the aluminum shaft is untwisted, while the steel shaft is twisted. Since the material should behave elastically and both shafts are fixed at one end, the steel shaft end tends to go back to its untwisted state. The steel shaft would want to go back to its initial position because it behaves elastically. However, since the two shafts are already connected by the pin, the steel shaft could not return to its original position, and it would only twist by an angle lesser than the angle of the mismatch. As the steel shaft twists back, it also brings the aluminum shaft along with the twisting. Actually, what hinders the steel shaft to twist back to its initial steel position is the aluminum shaft. Now, since we are interested with the torque felt by both shafts after the 750 Newton meter torque is removed, let's look at the free body diagram of the shafts. First, we look at the final whole free body diagram of the system. When we say the whole free body diagram, it means that we will not detach the steel shaft from the aluminum shaft and the pin is still there. Note that this is the diagram after we have removed the 750 Newton meter torque. Hence, we will not be putting a 750 Newton meter torque at this end. If there is no 750 Newton meter torque here and there is no torque there, we will not develop a reaction at the fixed end. And this is the whole free body diagram of the system. No external torques. Then, if there are no external torques, what causes our shafts to twist back? Again, here is the whole body diagram for the steel and aluminum shaft assembly that is connected by the pin. I reiterate that there are no external torques in this diagram because we have removed the 750 Newton meter torque. However, I have discussed in the previous slide that the body will move or will twist because the property of elasticity gives the tendency for the steel shaft to go back to its original position. Hence, when we dismember the assembly, we should have torques placed on the steel shaft and again another torque placed on the aluminum shaft. Note that the two torques are equal and opposite in direction because the pin only connects two materials, the shaft, the steel shaft, and the aluminum shaft. Hence, by the law of action and reaction, the torque felt by the steel shaft should be equal to the torque felt by the aluminum shaft. Note the directions of the torques. The torque felt by the aluminum shaft is towards the member, hence it is clockwise. And as I have shown in the previous slide, the aluminum, actually both the aluminum and the steel shaft will twist clockwise because that's the tendency of the steel shaft to go back to its original position. So the steel shaft wills the aluminum shaft to rotate clockwise. Now, why is the steel shaft experiencing a counterclockwise torque? This counterclockwise torque is actually the reaction of the aluminum towards the force exerted by the steel shaft to it. Again, while the steel shaft forces the aluminum to rotate clockwise, the aluminum resists this motion, hence exerts a counterclockwise torque to the steel shaft. When we draw the FBD of the pin, we have the clockwise torque from the steel shaft because it wants to go back to its original position. And we have the counterclockwise torque for the aluminum shaft. Again, note the law of action and reaction. We have the diagram of the steel shaft and the diagram of the pin. The torques should have opposite directions. Hence, from these diagrams, we have established that the torque in the steel is equal to the torque in the aluminum. As I've said, we would not be using the original equations that I have stated at the start of this lecture. So for shafts composite shafts that have initial mismatch, and you will remove the torque after aligning the mismatch, the torque in the steel shaft would be equal to the torque in the aluminum shaft after the removal of the torque to remove the mismatch. Now, we want to solve for the torque felt by both shafts, or the T steel and T aluminum. But our only equation as of now is that T steel is equal to T aluminum. And we have also solved for the angle of the mismatch. How can we solve for T steel and T aluminum? We need another equation. So again, we have here the cross-section of our shaft assembly with the blue circle being the steel shaft and the gray circle being the aluminum shaft. So this is the initial position of the aluminum shaft and this is the initial position of the steel shaft. What I'm drawing here is actually a deformation diagram, but this is a torsional deformation diagram. So we would be tracing what happened to the material. So the first step would be the closure of the mismatch. And we have here the angle of the mismatch, and we will label this also as phi st sub 1. So this is the first angle of twist that the steel shaft experienced. It's counterclockwise. And then, after the mismatch is closed, So what I have demonstrated earlier, the steel shaft would want to go back to its original position. However, it would not be able to go back to its original position because of the resistance of the aluminum shaft. Hence, we have the red line as our final position of our aluminum and steel assembly. So this is the movement or the angle from the initial position of the aluminum to the final position of our assembly is actually the angle of twist of aluminum. And it's also the second angle of twist of steel. Now, the net angle of twist of aluminum is this angle because that's the only twisting that the aluminum experienced. However, for the net angle of twist of steel, we have the original angle of twist of steel or the angle of mismatch, phi steel sub 1, minus the phi steel sub 2. We are subtracting the angles or we are subtracting phi steel sub 2 from phi steel sub 1 because they have different directions. One is counterclockwise and one is clockwise. As you can see from the diagram, phi steel net plus phi aluminum is actually equal to the angle of the mismatch. So this is the second equation that we need. The first equation that we have is T steel is equal to T aluminum. We have solved earlier that the angle of mismatch is 0.112 radians, and we will use it to complete the equation. So here is our equation. 0.112, or the angle of mismatch, is equal to T steel times 3 all over J of steel times G of steel plus P aluminum times the length of aluminum, which is also 3 meters, all over the J of aluminum. The aluminum, take note, is a hollow shaft. So we have this equation. And 28 times 10 to the 9 Pascal is the modulus of rigidity for aluminum. So since T steel is equal to T aluminum from this equation, we get this value. Note that the T steel here is actually the net torque that the steel have experienced. This already includes the 750 and the final torque that the steel has experienced. So it's 251.705 Newton meters. Thank you for listening and watching this video.